This week we're looking at how to determine a rate law for a reaction. As you recall, rate laws relate the rate of a reaction to a rate constant K times, in this case, hydrogen peroxide raised to some power we don't know but want to determine experimentally, and iodide concentration, which we want to raise to some power we need to determine experimentally. In order to do this, we need to hold one of these concentrations constant in order to explore what the rate dependence is upon the other reactant. So I'm going to start off by holding hydrogen peroxide constant, which essentially lets us look at experiments from the perspective of rate constant K prime, and it's K prime because we're holding peroxide constant. And we have iodide minus raised to some power of x. What we're looking to do is determine the exponent graphically based off 3 experiments. And so what we would do normally is make a plot, but since there's an unknown exponential, what we have to do is find a way of making that exponential linear. So what we do is we take the natural log of the equation, so we have the ln of the rate equals ln of, in this case, K prime plus x ln I minus. Oops. So here we have a form which will give us a linear relationship when we plot the natural log of rate as a function of concentration of I minus. And so you'll get 3 points. And from those 3 points, what you want to do is make a trend line. So we're talking about an XY scatter plot. And we need to add the trend line and equation. And from this equation, we'll get y equals mx plus b. Well, in this form, our y value would be the natural log of rate. Our intercept would be the ln of K prime, which is really nothing we need to worry about, but that would be the y-intercept. And the exponent x is our slope, with the natural log of I being essentially x in this equation over here. So now we can graphically determine what the exponent is, either first, second, 1.5, a third. It's all based entirely on the slope of that line. So now we've got the exponent x determined. We can do the same thing for the peroxide. Again, we will have natural log of H2O2 plotted as a function of rate. This 2 will give us 3 points, which we can make a line from. And again, the slope of this line is the exponent of peroxide. All right, well, that tells us how to graph this, but we need to figure out what rate to base this reaction off of. And so what we're going to do is we're going to relate the rate to the formation of iodine, that is naturally occurring iodine or atomic iodine. So I'm going to scroll this down. And so what we have to do is find the rate in terms of I2. Now I'm going to tell you right now that the I2 production is based entirely on the S2O3. And I believe it's a -2 ion here. So you have to use stoichiometry to change S2O3 to I2, molarity. And then you will divide that by the time of the reaction, and that will give you the rate. So we've got the reaction showing the relationship between I2 and S2O3. And so what we'll have to do is take the volume of S2O3 2- and multiply by 1 liter and X moles. You guys know the molarity of this. And then you can go for every 1 mole of S2O3, there is 1 mole I2, and that'll give you moles of I2. And then to get the rate, just take moles of I2, divide it by the time, and you now have your rate. So you'll have to do that for every single experiment, both in part 1 and part 2. So this shows you how to get the rate of the reaction. So keep that in mind. Hopefully that makes things a little easier. So for part 1 of the experiment, you have to determine the rate for the 5 experiments, and then use those rates to plot the natural log of the concentration as a function of the natural log of the rate for both iodine and H2O2 or peroxide, so you can ultimately end up with your rate law. So you'll need your rate law in order to do the second part of the experiment, but hopefully this gives you a good position to start off with and a little bit of the background as to how to set things up to do this.